Welcome back. Today we are doing 9.3 trigonometric models. Today we are going to be using the textbook Functions Modeling Change, a preparation for calculus 4th edition. It might be a little different from what you've been seeing up until now, but because information is kind of hard to just summarize really easily, I'm just going to use the textbook itself. Okay, let's get started. Okay, first we're going to take a look at the sums of trigonometric functions. So the first we are giving an example. So the first example shows mathematical models involving the sums of trigonometric functions. We see how the identities enable us to predict and explain the observed phenomena. Okay, so if we have two trigonometric functions, let's say p1 equals 40 minus 15 cosine to the pi over 12t, and this, I'm not going to read that because it's too long. Okay, so how do we add these? This is pretty much the problem that this question is asking us. So since it's basically asking us for the sum of these two trigonometric functions, this is what it's going to look like. So then how do we exactly now get the final answer from this? How do we add sine something and cosine something and make it into one? Well, it's actually pretty simple. We're going to use just what we learned before, how we add sine and cosine. First, finding the amplitude by adding the coefficients of each sine and cosine, the squared, and square rooting all of them. So that's going to be 18.028 megawatts. And how to find phi here, the angle of this trigonometric function. So we're first going to take tangent phi and do the coefficient of cosine over the coefficient of sine, so that is minus 15 over 10, which is going to equal negative 1.5, and then therefore the angle phi is going to be negative 0.983. Now, to consider whether this is going to be plus or minus, we're going to take a look at cosine phi and sine phi, which they've done here. And this is basically doing, for cosine phi, it's basically doing the coefficient. I'm going to write coefficient as CF, coefficient of sine. Oh, my bad, that's not the coefficient. Well, it turns out it was the coefficient of sine over, since it's 10, you can see here, negative 15 here, over the amplitude. I'm just put it as A, and it's the same for sine phi. It's going to be the coefficient of cosine over the amplitude, and based on whether this is positive, negative, or negative positive, this here is going to be either positive or negative. So basically what we're doing is we're using this here to solve the sum of trigonometric functions, since as you've seen in the example question, this was how it looked like. So we found the amplitude, the phi, and determine the angle by cosine phi and sine phi. So if you keep this in mind, it's not going to be hard to solve those problems as we've seen before. So moving on, we're now going to take a look at damped oscillation. So what is damped oscillation? Well, if we take a look at an example down here, we can see that first of all d is going to equal the value that represents the wave's displacement from its rest position, which is going to equal d. And if we put this into a graph, it's pretty much going to look like this. It's going to be different whether you use sine or cosine. So if it starts from a particular height, then it's probably going to be sine. It's probably going to be cosine, and if it just starts from 0 like this, then this is probably going to be sine. Yeah, so if you just keep that in mind, it's not that hard. But if we now go down here, it's going to talk about a decreasing amplitude, because especially for damped oscillation, we talk mostly for springs like this. But we know that a spring, once it starts bouncing, it doesn't go on forever. So to make it realistic, we have to use a decreasing amplitude. And when it's when it's in a linear form, it's going to be 5 minus the time. Basically, it's going to be like the distance minus the time. But if we do it that way, the problem is that after that certain amount of time, after 5 seconds for this problem, this is how it's going to look. It's not going to just decrease, but it's going to go back again like this. So we need to find a way how to decrease this in a much slower way. So how do we do that? We make an exponential function. As you see here, we're going to make an exponential function with a decreasing amplitude. If we do that, this is how the graph is going to look, and it's going to not exactly reach 0, but it's going to have an amplitude at 0 near 5 seconds. So this is what we're looking for. Therefore, what they're basically saying is that if a initial, b and c and k are constants and k is bigger than 0, a function of the form should be either this or this. Like I said, we can use sine or cosine based on where it starts from. Continuing on, now we have an oscillation with a rising midline. So what is that? If we take a look here, we can know that the midline is r equals 10,000. That's not hard to know. But when we have a damped oscillation, the problem is that as the value is going to get larger from r equals 10,000 plus 50t, as r equals 10,000 plus 50t minus 5,000 cosine pi over 6t, the midline is also going to rise with that graph at r equals 10,000 plus 50t. So that's basically what a rising midline of a damped oscillation means. It literally means that it has a rising midline, that the midline is not going to stay linear at still like this, but it's going to rise as the value goes on. So that's just what it means. Okay, so that was 9.3 trigonometric sums, and I hope that was somewhere near approachable. We covered about 3 parts from this section, and I guess I'll just have to hope to see you next time. Thank you.